Tesla turbines. Nikola Tesla, one of the most influential figures in the history of science and technology, was a Serbian American inventor, electrical engineer, mechanical engineer, and futurist, best known for his contribution to the design of modern alternating current electricity supply system. One of his least known inventions was the Tesla turbine, a centripetal flow turbine patented in 1913. The term turbine here could be misleading due to the absence of blade, since almost all turbines have blades. The Tesla turbine differs from typical turbines in that instead of using curved blades like those of a windmill, it uses smooth, parallel discs placed evenly across a shaft like series situated along a stick. He attempted to compete with the increasing popular piston engines in the early 1900s with this turbine when combustion engines were anything but reliable. Tesla believed that this turbine would have higher efficiency compared to other turbines and lower production costs as well. Now, let us check out how this turbine works.
Let us understand the working of the Tesla turbine. If you produce the viscous force tangential to a disk, it will start to spin. That's the simplest form of Tesla turbine. But that's very inefficient. The Tesla turbine mainly consists of a disk and a casing around the disk, which has an inlet and an outlet for the flow of fluid. The fluid enters through the inlet and eventually goes out through the outlet. When the fluid particles are rotating, they need a certain amount of centripetal force to maintain that motion. A fluid particle of same velocity requires more centripetal force near the center than away from it. For this reason, the rotating fluid particle have a tendency to move away from the center. As the velocity of fluid increases, the curvature of the path of the fluid increases, which leads to motion of fluid in spiral shape. The spiral shape increases the contact area between the fluid particle and the disk surface, thus increasing the viscous force production on the disk. This effect also means that the faster the turbine rotates, the more energy it will extract from the fluid. To understand the improved design of his turbine, we need to understand a key concept called as boundary layer thickness. Consider any fluid flowing over a surface. The fluid particles which are closer to the surface will adhere to the surface and the next layer will try to pull particle of this layer. In this way, you can clearly observe a velocity variation. The region up to which this velocity variation exists is known as boundary layer region. So the layer closer to the surface produces a drag on the neighboring layer, and as we move away from the surface, the drag force decreases and eventually becomes zero. To make this turbine more efficient, Nikola Tesla brought the disk closer, keeping the gap approximately twice the boundary layer. Here, no free flow occurs. The boundary layer region are touching each other, and we can see the shear effect are now dominant in between the disk space.
Even though Nikola Tesla promised efficiencies reaching up to 97%, the actual turbine could only provide efficiencies of around 40%. This was due to the limitations in the rotation speed. In order to reach the high efficiency, the discs in the turbine had to rotate at very high RPM, going up to 35,000 RPM. At this speed, the discs were not strong enough to withhold the centrifugal force acting on it. This caused disc warping. So, Tesla had to reduce the RPM to around 9000 RPM, change the diameter of the discs and the spacing between them. This affected the efficiency, which came down drastically to around 40%. Also, Tesla planned to use steam as the fluid in the machine, but steam engines and similar products were already being phased out at the time during the 1920s, and internal combustion engines were being developed. In the end, the Tesla turbine couldn't compete with the innovation and aggressive marketing of internal combustion engines and became obsolete in the end.
However, due to certain drawbacks, Tesla turbine was not found to be much efficient to be used on a large scale. However, Tesla turbines were reversible, and on supplying external energy with the help of motor, it can be used as a pump. And since Tesla turbine was using viscous property of the liquid, it is very much used in high viscous liquid field, such as in wastewater plant and in petroleum industries. If in for the future, if we overcome the wrapping of the material used in the Tesla turbine, it can still be used as a good efficient turbine.